Section 5.2 is definite integrals. So first we're going to do is look at sigma notation. This notation says that we are finding the sum. The Greek letter sigma stands for sum in mathematics. The sum of every term, a sub k, as k goes from 1 to n. So we're adding a whole bunch of sums up. A sub 1, a sub 2, a sub 3, all the way through to a sub infinity. All this is saying is that, as we've been doing, when we have some integrals, we're going to add up all these sums. When we've done Riemann's, we're going to add up all these sums to get our area. The difference now is we're going to do an infinite number of Riemann sums. So let f be a function defined on a closed interval a to b for any partition P of a through b. Let the numbers c sub k be chosen arbitrarily in the subinterval x sub k minus 1 to x sub k. Just copy it down for now. If there exists a number I such that the limit as the subinterval approaches 0 of the sum of all my subintervals, the function value times the width of the interval, then that value I, no matter how P and the C sub k's are chosen, then f is integrable or able to be integrated on the interval AB, and I is the definite integral of f over AB. Copy it down and I will explain it. So I've got a function that I am going to call f of x from A to B. We are now going to choose a subinterval from some x value to another x value. And that subinterval, we're going to call it P. Now, as P approaches 0, in other words, as these subintervals get closer and closer, skinnier and skinnier, okay, so that delta x approaches 0 as well. And no matter how small I make the interval, if I pick a function value in the interval, and I do my width times my height, just like I've done for my Riemanns, and I add these all up, I will get a value I that we call the integral. The integral, and in this case it's a definite integral, we'll talk about indefinite integrals later. The definite integral is equal to the area. So our Riemann sums give us an approximation. If I take the limit of the sum of all my rectangles, that's my height times my width, as these intervals get skinnier and skinnier and skinnier, then I'm finding an integral. So just like you did with your derivatives, you kept getting the derivative closer and closer to the point until you found an actual derivative. So we're doing the same thing with our areas. We're making our rectangles skinnier and skinnier until we find an actual area. All continuous functions are integrable. That is, if a function f is continuous on any interval ab, then its definite integral over ab exists. As long as there are no gaps in the function, I can find the area. As long as it's continuous, I can find the area. So the definite integral of a continuous function. Let f be continuous on AB, and let AB be partitioned into n subintervals of equal length. So I'm going to take my interval from A to B. I'm going to find that distance, B minus A, and I'm going to divide it by n intervals. The definite integral of f over the interval AB is given by the limit as n approaches infinity, more and more and more and more rectangles. As k goes from 1 to n, so from whatever number to an infinite number of n's, of the function value times the width. Our dx, no matter how skinny it gets, is still my width, and my function value at any particular point is still my height. where C sub k is chosen arbitrarily in whatever subinterval we are dealing with. So this is another way of writing it. So we're saying that the width, that the number of intervals becomes infinite. In the last notation, which was very similar, we said that the interval itself became skinnier and skinnier and approached 0. Now we're saying that the number of intervals becomes infinite, therefore the width also approaches 0. Another way of writing it. All right, so the definite integral. This is how we are going to change that sum notation into integral notation. So instead of saying the limit as n approaches infinity of the sum as k goes to infinity of f of c sub k times delta x, we are now using this notation. There's my a to b, that's my interval of the function differentiated along the x-axis. My x-axis has my little dx's. So a much shorter way of writing it than this. It means the same thing. We read it as the integral from a to b of f of x dx, or sometimes the integral from a to b of f of x with respect to x. So dx means with respect to x or just dx. So the integral from a to b of f of x dx means that for my f of x function, from a to b, I am going to find my area. So again, here are the parts of our integral. The integral from a to b, the lower limit of integration, the upper limit of integration. The distance on my axis across which I am calculating my area. The integral sign is just saying that we're finding the sum. We're summing up all of our rectangles for the function f of x using little dx pieces. So when you find the value of the integral, you have evaluated the integral. And we'll talk a lot more on how to do that as we move along. So using notation, changing this information to an integral notation. The interval from -2 to 4 is partitioned into n subintervals of equal length. Delta x equals 6 divided by n. 6 is my distance from -2 to 4. I'm going from -2 to 4. My total distance is 6. I'm dividing it into n pieces. Let m sub k denote the midpoint of some interval. So I choose some interval and I use the midpoint. This was our c sub k in the last notation. Express the limit. So first, writing it as a limit, the limit as n approaches infinity, a whole bunch of divisions, and k goes from 1 to n. So n starts off as one big subdivision, then 2, then 3, then 4, then 5, until we're skinny, 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 of the function evaluated at some random point times delta x. So there's my limit notation. I want to change this to an integral. So what I'm going to do is rewrite this as the integral from -2 to 4 of the function evaluated with respect to x, or the integral from -2 to 4 of 3x squared minus 2x plus 5 dx. So we've now learned a new notation that represents all of these little rectangles being added up. And the rectangles are infinitely thin right now. So what does this mean? So the area under the curve is our definite integral. All that notation means is we're finding the area under the curve. If y equals f of x is non-negative and integrable, which means it's continuous, over the interval ab, then the area under the curve of y equals f of x from a to b is the integral of f from a to b. All this is saying is what we said over and over. If I have a function y equals f of x from a to b, then the integral equals the area. Now, what if the function is below the curve? So if my function is down here, and I'm going from A to B, then the area is going to be the opposite of this integral. Since these function values are all going to be negative, when I find the sum of these rectangles from A to B, I'm going to get this as a negative value. The area is the opposite of that negative number. If the function, so that's this top part, if the function goes both above and below the axis from A to B, then the area above the axis, which will be a positive integral, minus the area below the axis, which is going to be a negative, will give you a positive plus a positive, and it will give you the whole area. Again, we'll do some like this together in class. So the integral of a constant, we talked about this way back at the beginning. If our function is a constant, c, then all I have to do is multiply c, which is my height, times the width, or the interval from a to b, which is my b minus a. So the integral from a to b of a constant dx is simply the constant times the distance that we're integrating over. Same thing holds true, but if our value for c is negative, we use the opposite of c, make it positive, so we can find an area. All right, we will do examples of all of these in class. I want you to do one more thing. Get your calculator out. So something like this, when I want an infinite number of rectangles, is difficult to do until we know how to actually integrate algebraically. So for right now, we're going to use your calculator. Get your calculator out, hit Math, and choose number 9, which should say the integral, so Math 9, which should say the integral, oh no, it says FNINT first. FNINT of something. In other words, we're finding the integral over an infinite number of sections. I'm not sure that they all say it this way. Yours might say something a little bit different, but choose Math 9. Okay, most of you will get something that looks like this. So, in here, we're going to put our limits of integration. In this case, -1 and 2. So once you get this on your screen, plug -1 into the first box, 2 into the top. In here, we're going to put our function, x sine x, and in here, we're going to type another x. If you push enter, you should get 2.04. That is the area under this curve between -1 and 2. Some of you, not many, will get something that looks like this with a parentheses. If your calculator gives you this, you're going to put your function in first. You're going to say you want to evaluate x from -1 to 2. You will still get the same answer. Okay? So just try this on your calculator, see if you can get it, and we will do plenty of examples and talk about this in class.